Hello students, today we will study about the working of MOSFET and fabrication. After that we are going to study about the fabrication of CMOS inverter. So let us start one by one. As we see here in MOSFET of enhancement type, we have source, drain, channel, gate terminal separated from channel with thin SiO2 layer. The entire thing is held in a substrate material. As we see here, this is N MOSFET, hence source and drain are N type, substrate is P type, and gate material is made of polysilicon. So in the beginning, why did we call this as enhancement? In enhancement, the channel is not present at the time of manufacture. It is created by establishing a positive voltage between gate and the source. So when we apply a positive gate electric field between gate and source, the minority carriers in the substrate are attracted towards the gate terminal and get collected in the surface region, and hence this region will now have more number of electrons and act like n-type material. This process is called charge inversion, and a minimum of threshold voltage is required between gate and source to establish the channel. Initially, as long as VDS is equal to 0, there is no current flow. And once we apply a positive voltage between drain and source, we can expect current to flow between drain and source as electrons flow between source and the drain. As we increase the drain to source potential, the amount of current that flows between drain and source increases. The region of operation of the MOSFET is said to be non-saturation region of operation. In this region, the current is proportional to VGS as well as VDS. But when the voltage applied to drain with respect to source equals to the voltage that is applied between gate and source, that is, when VDS is equal to VGS minus VT, then at the end point we can expect the charge or the free carriers to be depleted. The channel gets pinched off at this point as the positive gate electric field is not sufficient to keep the charges inverted, and the current now becomes constant because of the channel getting pinched off, and the current now that flows is the diffusion current. As we further increase VDS above this point, what happens? The pinching of the channel occurs at an earlier point. Now, when once VDS exceeds VGS minus VT, the device is said to be in saturation region, and in this region the current is constant and it no more changes with increase in VDS, or it remains, in other words, it remains constant. So we could see three regions of operation, that is when we don't apply positive gate to source voltage, there is no current flow. The region of operation is in cutoff. When once we apply a voltage which is greater than the threshold voltage, then only channel is established in enhancement device. Whereas in depletion device, the channel is already present. Next, we'll see how a N-MOSFET device is made. You need to know that this N-MOSFET is made from silicon, which is obtained from silica that is available in the nature in abundance. The silicon, initially what we obtain should be very pure, and it is now in the molten state in a crucible, and a little silicon which is called the seed is attached to a rod, and the rod is dipped into the crucible which contains molten silicon. As we pull the rod outside, the silicon comes out in the form of a rod, and which is now called an ingot. The wafers are created from ingot by slicing the ingot into thin wafers with the help of a diamond shaped or diamond tip tool. And once we obtain the wafer looks like this in the side view. So the wafer can be either P-type or N-type. In this case, since we are using NMOS fabrication, the wafer will be P-type substrate. So next, we have to define active region of the N-MOSFET. The active region holds the source, drain, and channel of the MOSFET. The pattern of the active region should be defined over the chip. So how do we do that? We can do that with the help of photolithography process and chip chemical etching. So when we cover the entire surface with photoresist material, after SiO2 is grown by oxidation method, we can subject this for light source, and then the region where the substrate is exposed, photoresist material will be hardened, and the region where it is not exposed, it will be unaffected. So below the unaffected photoresist material, the SiO2 layer can be etched out by making use of chemical etching process. And once we remove the SiO2 region, the active region is defined. So next step is to grow thin SiO2 layer of the thickness of 1 micrometer over this. 0.1 micrometer around over this. Then polysilicon is deposited over the entire surface by using chemical vapor deposition method. So the gate region is patterned from polysilicon with the help of photoresist layer using photolithography process and chemical etching and a mask. We can pattern gate structures, and once the gate structure is patterned, we can see the gate here placed over the thin layer. Using the same mask, the unwanted SiO2 is also removed and creating areas of diffusion. So the portion now is subjected to diffusion to create source and drain regions. Once the source and drain regions are created, it looks like this, and then again you cover the entire surface with SiO2 and pattern holes so that you can establish contacts. And once the contact cut holes are created with the help of photolithography and chemical etching, you cover the entire surface with metal using metallization procedure. And then you can remove metal from unwanted portions and retain metal where it is required. So interconnection of the circuits are done at this stage. After this, entire surface is covered with passivation layer and pins are stitched externally. Hence, N MOSFET is created. Next, we can know how CMOS fabrication can be done. As we know that in a CMOS inverter, we have one N MOSFET and one P MOSFET. So, in P well process, first the substrate is taken and subjected to oxidation to grow SiO2 layer, and using photolithography process, P well region is defined. And also you have to use chemical etching to expose this region for diffusion. So when once it is subjected to diffusion to P type of impurities, that is boron, you create P well. The size of the P well and the doping level will determine the resistivity of the P well. After P well is made, you have to define active regions of both N MOSFET and P MOSFET. That is done with the help of photolithography process and chemical etching. Then the entire surface is covered with thin SiO2 layer, and then you have to deposit polysilicon over the entire structure by making use of chemical vapor deposition method. And again you have to use photolithography and chemical etching to define the gate structures in the chip. Using the same mask, you can remove unwanted thin SiO2 from the other regions where you have to create source and drain. The next, you have to use P plus mask in order to create P type source and drain for P MOSFET. This is done by subjecting this portion to diffusion. As this portion is exposed, impurities of P type like boron get embedded, or they get introduced into this layer, and self-defined source and drain regions are created. Next, a negative of this mask, which is P plus mask negative, is used to create source and drain regions of N MOSFET. So this is again done by diffusion, and N type of impurities, that is either phosphorus or antimony, can be used. Once source and drain regions are created, you have to create contact cuts by making use of thick SiO2, photolithography process and chemical etching, and then carry out metallization to do the interconnection. So after this, the complete CMOS circuit or CMOS inverter is ready. So, but before that, you need to cover the entire surface with passivation layer, allowing only the pins to be connecting to the contact terminals. This is about P well fabrication. Thank you.